You all knew what was in there. A gyroscope. A heavy, symmetric disc, free to rotate about this axle. And now we've named it. But that's all we've done. We certainly haven't explained it. And if we want to go on to understand how it works, we have to learn something about the motion that causes it. This spinning motion. Before we go on to an explanation, though, let me show you the same thing with a larger wheel, where it'll be much easier to see. There's nothing special about this connection. 2 thumb screws to hold the bicycle wheel axle, a pivot free to rotate, and a low friction bearing. The observation we have to make is very simple. A wheel which isn't spinning, when released, falls, as it should. However, if the wheel is spinning, it doesn't fall, but instead moves about the pivot with a characteristic motion called precession. Let me show you one other thing, though. When I first drop the wheel, it does fall a bit and then recovers, and in fact precesses about the pivot with a bobbing motion called nutation. We won't be concerned with nutation. Let's watch the precession once again. Now let's go on with our explanation. We can consider this wheel to be made of separate particles, each moving in a circle about the axis. Let's fix our attention on one of them. Suppose we consider this particle, for instance. Its mass is m1. Its distance from the axis, r1, and it's moving this way with a velocity v1 perpendicular to this radius vector. We can write its angular momentum. Its angular momentum is L1 equals the linear momentum m1 v1 perpendicular times r1. We can also express this angular momentum of the particle in angular language. But to do that, I'll have to rearrange these 2 factors. Writing this again, L1 is equal to M1 R1 V1 perpendicular, the same expression as we had before. And now if I divide V1 by R1, and of course multiply by R1 to keep this expression the same, getting an R1 squared, this expression for the angular momentum breaks into 2 factors very naturally. The first, what we call the moment of inertia, and the second, the angular velocity of the wheel. So, writing the angular momentum of this particle again, L1 is equal to J1, the letter given to the moment of inertia of the particle, times omega, the angular velocity of the wheel. We've now computed the angular momentum of this particle. We could do the same for one here, or one there, or one here. In fact, for every particle in the wheel. And when we do, we can find the total angular momentum of the wheel by adding all these separate angular momenta together. Let me write the expression for that addition. The total angular momentum of the wheel is equal to L1, the angular momentum for the first particle, plus L2 for another particle, plus L3 for another particle, plus, and so on until we've added all the particles. A more convenient and a shorter way for writing this would be to write L is equal to the total moment of inertia of the wheel, which is the sum of the separate moments of inertia, times omega, the angular velocity of the wheel. Notice that the angular momentum is directly proportional to the angular velocity. We now know how to compute the angular momentum of this wheel. But there's something I haven't told you. This wheel has an angular momentum which you could compute. And if I were careful about the way I spun it, spinning it with the same speed, this would also have an angular momentum, which might be exactly equal to the one we just had. But it's spinning in the opposite direction. Does this make a difference? Yes, it does. Let me show you that it does. Spinning it one way, and now the other. The precession is different. In order to designate these two directions of spin, a right-hand convention is used. The fingers of the right hand follow the particles around the axle, and the thumb of the right hand points out the direction of an imaginary arrow used to designate this spin. When the wheel is spinning in this direction, the fingers following the particles around the axle, the thumb pointing out the direction of the imaginary arrow, which designates the spin. Let me use a real arrow to illustrate. When the wheel is spinning as it is now, the arrow goes in this way. On the other hand, when the wheel is spinning in that direction, fingers following the particles, thumb pointing out the direction of the spin, so my arrow had better go here. And again, there's something I haven't told you. Once I have the wheel spinning and know the magnitude of the angular momentum and even know which way it's spinning, there's still a matter of orientation. This is one. Here's another orientation. And this one, or that one. Does that make a difference? It too does sometimes, which I'll show you by using another wheel. Here I have a wheel whose orientation I'll be able to change while keeping the wheel at the same distance from the pivot, changing nothing but the orientation. Let me spin the wheel now and release it. The wheel precesses with some nutation. Now, carefully, what I'd like to do now is do nothing but change the orientation of the wheel. And I change the orientation of the wheel by 90 degrees, no more. Turn the wheel, changing its orientation with respect to this pivot by 90 degrees. Now watch. Spin it, equally hard, I'm sure, and I drop. So the orientation does make a difference. Now, if we have a spinning wheel, we can compute the magnitude of the angular momentum, and we can designate the direction and orientation of the spin. What we have here very much resembles a vector quantity. Is it a vector quantity? Does it behave like a vector quantity? Let's go to some other wheels and see if it does. What I have here is a single shaft on which are mounted two bicycle wheels. If I spin this one in this direction, precession. If in addition I spin the second one in the same direction, two spinning wheels behaving as one. However, if I spin this one in this direction, and as nearly equally as I can, this one in the opposite direction, two spinning wheels behaving as if neither were spinning. And yet when I remove the canceling angular momentum, precession, as before. These two angular momenta seem to add, and they certainly did cancel. But we had a special case here. Both of the vectors were along the same straight line. So we have to carry our test a bit farther. On the table, we have an apparatus which consists of 3 motor-driven gyroscopes, each with a separate control unit. The 3 gyroscopes are mounted on an unbalanced plastic plate, free to rotate about this pivot and free to fall. What I'd like to do is to see whether the 3 angular momenta can be made to add to 0, in spite of the fact that they are not in the same straight line. In order to do this, I'd like to try to add this angular momentum to this angular momentum and see whether the middle angular momentum can cancel the other 2. So let's start the outer ones. First, starting this one in this direction, angular momentum that way. And now this one in this direction, angular momentum that way. And while they're coming up to speed, let me remind you of something. The angular momentum of a gyroscope is directly proportional to its angular velocity. So that if I measure the angular velocity of a gyroscope, I'm measuring the angular momentum as well in some arbitrary unit. In addition, these 3 gyroscopes have been carefully made so that their moments of inertia are equal. This being the case, if I measure the angular velocities of these 3 gyroscopes, I am measuring their angular momenta as well in the same arbitrary unit. It's coming very close to being at the speed I'd like to have it. Let's try something. There. Now, what have we? Let's go to the meters and see. Meter number 1, which reads the angular velocity of the first gyroscope, reads 5,000 revolutions per minute. Let's call that 5 arbitrary angular momentum units. Meter number 3, which reads the angular velocity of the third gyroscope, reads 5,000 revolutions per minute. Also 5 arbitrary angular momentum units, whereas the second gyroscope isn't turning at all. Now that we have this information, let's analyze the situation. We'll represent the angular momentum of the first gyroscope by this vector and label it L equal 5 arbitrary angular momentum units. Of course, gyroscope number 3, having the same number of arbitrary angular momentum units, will also be represented by a vector of the same length, but in this direction. This angle has been chosen conveniently so that these vectors will resolve by a 3, 4, 5 triangle. I'll resolve the first. 3 units in this direction. And 4 here. I've now replaced this vector by its components. And the same for the second vector. 4, 3. These 2 vectors, pointing in opposite directions and of the same magnitude, of course, cancel, leaving only these 2 to be added. 4 plus 4 in the same direction give a resultant of 8. So, angular momentum 1 plus angular momentum 3 adds to 8 units of angular momentum. 5 plus 5 giving 8. In order to cancel the angular momentum contributed by gyroscope 1 and gyroscope 3, gyroscope 2 must provide an angular momentum of 8 units in the opposite direction. And in this way, an angular momentum of 5 plus an angular momentum of 5 plus an angular momentum of 8 will add to 0. Our vector analysis has shown that the angular momentum of gyroscopes 1 and 3 add to 8 units of angular momentum in this direction. In order to cancel these, gyroscope 2 will have to supply 8 units of angular momentum in this direction. Let's start gyroscope 2. And watch it as it comes up to speed. (3,000) RPM, that is. 4,000, 5,000, 6,000, 7,000, 8,000. Is the angular momentum really gone from these 3 gyroscopes? It appears to be. Let's try something else now. Let's get rid of the angular momentum contributed by 1 and 3. Gyroscope 2 is now providing 8 units of angular momentum in this direction, whereas before 1 and 3 combined were providing 8 units of angular momentum in this direction. The angular momentum behaves like a vector. We'll treat it as a vector. So now we can write in vector form L1 plus L3 plus L2 equals 0. Now that we have an angular momentum vector, let's pause for a moment and see how the angular momentum vector is changed. Let's go back to the disk again, rotating about an axis. If I want to change this angular momentum, I apply a force at some distance from the axis, r. The torque that this force causes, T, is equal to the perpendicular component of the force, that is the force perpendicular to this radius, r, times the radius. So if the force were applied at half the distance, just as in the case of the lever, we'd need twice the force to cause the same effect. The torque causes a change in angular momentum, and the relationship between the torque and the change in angular momentum it causes, the torque times the time for which it's applied, is equal to the change of angular momentum it causes. But angular momentum is a vector, so the change of angular momentum is a vector. And we expect this to be a vector equation. There's no vector nature in the time, and so the torque must be a vector. We know its magnitude, and now we have to find out about its direction. We define the direction of the torque in the same way as we did for the angular momentum, using a right-hand rule, as follows. If the fingers of the right hand are made to point along the direction of the force applied, then the thumb of the right hand points out the direction of the torque. You see, this rule is good whether we apply the force here, closer to the axis, at this point on the wheel, in fact, at any point on the wheel. And you see that it does indeed work here, because this force applied in this way would cause an increase in the angular momentum of this wheel in this direction. A torque in this direction causes an increase in angular momentum in this direction. But we chose a particularly simple direction for applying this force. We might have applied it this way, or this way. In any case, the same rule applies. And now we're in a position to begin to understand the precession of a gyroscope. Here we have a gyroscope, very well balanced and mounted on gimbals. The gimbals permit the gyroscope to turn in any direction and in any position, assure that there'll be no torque acting on it. Let's put some angular momentum in this gyroscope. The wheel was turning this way, so the angular momentum vector points toward you. What would happen if I pulled down at this point? Let's try it and see. I'll use a kilogram. Now that we've seen it, let's explain it. The wheel was turning in this direction so that the angular momentum was pointed out here toward you. We applied a force downward at this point, which caused a torque in this direction. A torque in this direction causes a change of angular momentum in this direction. So, we had the original angular momentum pointed outward toward you, plus a change in angular momentum, which gives the new angular momentum along the shaft. The old vector plus the change in the vector, which gives the new vector. In fact, a good way to remember this is to think of it this way, that the motion of the angular momentum vector is such as to tend to align it with the torque vector. Let's see that again. Now, and again, but now, if I apply the force continuously, there's a continuous torque. A continuous torque makes a continuous change in angular momentum. And we have precession. It can also be shown that the rate of this precession depends on only two quantities, the angular momentum of the wheel and the torque we apply. Now that we've seen how precession takes place, let's try to predict its direction in this case. I'll spin this wheel in this direction. And so the angular momentum of the wheel will be pointed along the shaft in this way. The torque will be supplied by the force of gravity downward here and the force of the pivot acting on the shaft upward here, so that the torque will be in this direction. Which way will the wheel precess? This way or this way? Can you tell? Try it. Are you ready?